Hello. Today we'll discuss push-down automata or PDA. So, as we have seen that in finite automata, language of this form, suppose language L of G of the form a to the power n, b to the power n. So, n is suppose greater than or equal to 1, cannot be accepted because finite automata has to remember the number of a's or b's in the string. So finite automata will require an infinite number of states to accept this kind of language. Now to overcome this problem, additional auxiliary memory, which is basically in the form of stack, so stack is included. As also we know that in stack, the stored element are processed in LIFO, last in first out fashion. Last in first out fashion. Now to accept string of this form a to the power n, b to the power n given by a language L of G. So initially what we need to do, we have to push all the a's here, right? And onto the stack, suppose it is a stack. And when b's are encountered, the topmost a from the stack will be removed. Right. So when suppose we have 3a and 3b's, for example. So now the concept is when a's are comes, we have to push one by one. First one a, second, third. 3a's are pushed onto the stack, and when b's comes, we have to remove this. So we have removed this. Then when second b comes, we have to remove this, and third b reduce. In this way, equal number of a followed by equal number of b will be accepted. Thus, matching of the number of A and number of B's is performed. So, this type of additional arrangement in a finite automata, we call it as a push-down automata or PDA. So, difference is that finite automata, we have added a stack which is called an auxiliary additional memory. So it is the basic concept of the push down automata. Now we'll describe the push down automata. Right now, the description. Description. So a push down automata, a push down automata or automaton, push down automaton consists of number one, a read only input tape, a read only input tape. Second, input alphabet, input alphabet. Third, finite state control, finite state control with two heads. One read only and another read write. Another read write head. Number 4, a set of final states. Set of final states. Number 5, an initial state. And number 6, a stack a stack called pushdown store, or sometimes we call in abbreviation it is a PDAs or pushdown store. So this is basically the we can say that the component of a pushdown automata. Now graphically we can draw in this way. So this is our, suppose, the input string etc. It is basically the read only input tape, read only input tape, from where it will read. Now this is a finite state control. We can say it is a finite state control, finite state control. One head, it is a read only or read head, and it is a stack. We say it is a stack or PDAs or push down store, and suppose the symbols are Z0, Z1 and so on, and it is suppose ZK, it is ZK minus 1. So it is basically direction of store, direction of storing. Okay, and here it is a read write head, it is a read write head. Okay, and here the mechanism with a finite number of state, here it is a finite number of states. Some control mechanisms are also here there. So control mechanism, and suppose state 0, suppose state 1 and so on. So this is a graphical we can represent a push down automata or PDA or push down automata. So both this read and write operations are performed on this push down store. Here we can read as well as write operation can be performed. So when we insert, we call it as a push, and when we remove from the stack or PDAs, we call it as a pop. Now the transition from one state to another state in a push down automata is almost same in the case of finite automata. And the push down automata, on reading an input symbol from the input tape and the topmost symbol from the push down store, moves to the next state and write, or sometimes we call the push, a string of symbol into the push down store or PDS. Right? So this is the primary concept. Now we formally define the push down automata. So definition. So a push down automata PDA M, suppose it is a M, is defined as 7 tuples. Okay, so M is equal to Q sigma gamma del Q naught Z naught F, where Q is a finite non-empty set of states, a finite non-empty set of states. Okay, and sigma, a finite non-empty set of input symbols. and gamma, a finite non-empty set of push down symbol, that is symbols in the push down store. So basically symbols in push down store. And obviously we know the Q naught is initial state, and G naught is a special push down symbol. We call it as a initial symbol in PDAs or push down store. So initial symbol in PDAs, and F is the set of final state, the set of final state, that is F is a subset of Q, and delta, that is a transition function. So we call it as a transition function. Okay, and this transition function maps, so which maps from where Q cross sigma union null empty cross gamma to, or we can say map into the set of finite subset, of Q cross gamma. Note that this F, basically subset of Q, means maximum all the states will be the final state, or minimum there is no final state. We will describe more details because pushdown automata, here string can be accepted by final state or string can also be accepted by empty stack. Now this transition function, that is this delta, this transition function delta, it explains that pushdown automata is in any state queue and it takes the input from this input alphabet as well as null, means it may read, may not read. So it the pushdown automata in any state queue, it reads the input symbol from this set sigma union null and checks the topmost symbol from this gamma, that means pushdown symbol, so from this gamma, and as a result it makes a transition to the next state, which is Q, or a state in the set Q, and write a symbol or write a string denoted by this gamma star in the top of the pushdown store. So these are basically written on the top of the stack or pushdown store. Clear? Now few concept. So a finite automata with no final state has no significance, as we have seen that in case of finite automata, because it accepts no language at all when there is no final state. But it is not true in case of pushdown automata, because pushdown automata can accept language by null or empty store also. So it is not necessary that every time the reading head. So second concept is, it is not necessary that every time the reading head reads a symbol from that read only input tape. When reading head does not read anything from the input tape, then it is assumed to be null. So these are the two concepts which should be remembered. Number one, PDA can accept language by null or of the or empty stack, and second, when it does not read anything from the input tape, it is assumed that it is null. Now, language, language accepted by PDA. So, language of PDA. So, as we know, the context-free language and the regular are these languages which are accepted by the PDA. So, context-free language CFL and the regular are the languages which are accepted by the pushdown automata. Pushdown automata, as we have mentioned, that is similar to the finite automata. Only difference is that the PDA has additional auxiliary memory in the form of stack. Right. Now we will show the graphical notation for pushdown automata. So graphical notations for pushdown automata. At any time, the state of PDA, that is M equal to Q sigma gamma del Q naught Z naught and F, is given by this one. The state Q belongs to Q, the PDA is currently in. Number two, the input string, that is suppose X, belongs to sigma star, which still has to be processed. And number three, the content of the stack, that is pushdown store, is basically, we can say, alpha belongs to gamma store. Clear? So again I repeat, the state Q belongs to any state of Q. So pushdown automata is currently in, and X is a input string that belongs to sigma star, which still has to be processed, and alpha basically called the content of the stack, that is a pushdown store. Now based on this, we describe the instantaneous descriptions. So what is instantaneous description, or ID? Sometimes we call the ID or instantaneous description. Instantaneous description. Okay. So an instantaneous description, that is ID, instantaneous description, that is ID, is defined as Q X alpha. These are three tuples. As we have mentioned, that Q belongs to Q, means pushdown automata currently in, and X belongs to sigma star. This is basically a string, has to be processed, and alpha belongs to gamma star, is a pushdown symbols or the content of the stack, right? So the instantaneous description, this ID or this Q, X and alpha represents the present status of the pushdown automata. So this Q, X, alpha represents the present status of pushdown automata. Clear? Where the meaning is this Q is basically the present state, and X is basically the input string, and whose leftmost symbol will be scanned first, or which still has to be processed. Yeah, still has to be processed. And this alpha, basically the alpha, this alpha here it is called a string of push down symbol, a string of push down symbol, push down symbol or symbols, push down symbols. Okay. Now, what is the meaning of this? We can give an example here. Clear? So, suppose we assume that let one of the ID is Q1, A1, A2 up to suppose AK, Z1, Z2 dot ZL is. What is the meaning of this? It means the current state of the pushdown automata is Q1. The input string to be processed is A1 to AK, that is the input string. And the move of this pushdown automata or PDA in next state depends upon the present input, that is the leftmost symbol of the input string, that is A1, and the topmost symbol, that is Z1 of the pushdown store. Okay, so here Z1 is the topmost, it is a top, and A1, that is the leftmost symbol which has to be scanned first, and Q1 is the present state of the PDA, present state of PDA or pushdown automata. Now, based on this, we can define we can discuss the move relation. So now, move relation. Move relation. What is this move relation? So the transition, move relation means the transition from an instantaneous description, that is one ID, to another ID. So it is basically defined in terms of this move relation and denoted by this symbol. This is the symbol to denote the move relation. So what is the meaning in summary? The transition from one ID or instantaneous description to another instantaneous description is defined in terms of the move relation, and it is denoted by this symbol. Okay. Now, for example, we give an example. Suppose a PDA is in state Q1, okay, and the input string is X1, X2, suppose Xn, and the symbols in the PDAs are push down store Z1, Z2 up to ZL. Yeah. Again, I repeat, Q1 is the present state of pushdown automata, X1 to Xn is the input string, and Z1 to ZL is the pushdown store symbol or PDAs, where Z1 is the top most symbols of PDAs and X1 is the leftmost symbol that input that has to be processed first. Now suppose after processing, or if the push down automata goes to next state, let it is a q2, by scanning x1, we only scan x1 from this input string and writing a string u1 u2 up to suppose um, and we can also say suppose it is a beta. This string we consider that it is a beta. On place of z1, on place of z1, that is, it is a topmost, right? Topmost symbol of PDS. Then the move relation can be depicted by using this. Your present state is q1, and at that time string x1 x2 up to xn. At that time the symbols of the PDAs are z1 z2 and zl. So this is the present ID. We can say it is the present instantaneous description or present ID. Now after processing x1, that means this x1 has processed, and the automata push down automata moves to state q2, and already x1 processed, that means remaining string x2 to xn, and this is denoted by the move relation, this symbol, and in place of z1 it writes u1 u2 um. So we can write in that way here u1 u2 dot 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 um, then z2 and dot dot zl. Clear? So this in abbreviate we can say it is a beta. We can say it is a beta is a string. So it is the next ID. It is a next instantaneous description or next ID. Okay. Now this can be shown graphically by like that. It is read only input tape. Clear? So here x1 x2, it is a xn, and so at present this is a present state of the push down automata, and at that time stack PDAs symbols are zl, it is a z1 z2, and this is the read write head, so it is a read head and it is a read write head. So it is a present ID, or you can write present ID. Now after processing this x1 it moves, so it will be x2 x3 and so on, that is a xn. Now the read head is under the symbol x2 and your state is q2, and at that time the PDA symbols are u1 u2, it is a um, and z2, it is a zl. Okay, and redirected head is here, it is a read. So this is the next ID or instantaneous description. Clear? Now if we consider suppose q1 x alpha 1 is the present id, if we consider that it is a present, it is a present id, and after move more, after more than one move, you can say after more than one move, we get, suppose state is qm and input string to be processed is y and push down symbols are alpha 2. Then we can write in this way. This move relation can be written in this way: q1 x alpha 1. After more than one moves means this star. The automata will be in state qm and string to be processed y and alpha 2 is the push down symbols. And if the above move is exactly n, then we can write q1 x alpha 1, here n, we can write qm y alpha 2. That means here the precise number of moves are given, that is n. Okay. Now some properties of the move relation. Properties of move relation. Okay. Number 1, property 1, if q x alpha 1 after more than on moves reaches to some state q dash, at that time the string is exhausted and the topmost or push down symbols are beta, then for every y, that is the string belongs to sigma star, we can write q x y alpha more than one moves, it will be in state q dash, and here string exhausted, the string remaining string is y, and here it will be beta, and vice versa. Property number 2, if q x alpha after more than on moves is in state q dash and string is exhausted and push down stored symbol is gamma, then for every beta belongs to gamma star, that means push down symbol beta, you can write q x alpha beta more than on moves will be in the same state, string is exhausted, here it will be gamma beta. So these are the two properties of the move relations. Okay. Now how we represent this push down automata in terms of the transition diagram. So representation of push down automata by transition diagram. Okay. So by transition we can write, suppose this is a delta transition function. Suppose you are in a state, suppose qi, at that time your symbol is input is 0 and stack topmost symbol is suppose z0. So it is basically, we can write in that way, it will move to some state, suppose qj, and 0 z0 is replaced by 0 z0, we can write. And graphically we can write in this way, your state is qi, okay, and next state is qj, and your symbol is 0 z0, input is this, sorry, you can write in that way, and it will be 0 z0. Yeah, so it is basically push operation, 0 z0, it is a push, so we can write in this way. So or graphically we can represent in this way. Now we define how strings are accepted by pushdown automata. Now acceptance by final state. As we have mentioned that pushdown automata, we can accept string by using final state as well as by using empty stack. First we will discuss the string acceptance by final state. So the acceptance condition, conditions include that the input string must be exhausted as the PDA or pushdown automata reaches to final state. So let P be a pushdown automata which is of the form P is equal to Q sigma gamma del Q naught G naught F, and it is be a pushdown automata, and the set accepted by this PDA in terms of the final state we denote it by T of P, where W is basically the string of sigma star, and from initial state the string is W, and stack top symbol at that time initially Z0 is the initial topmost symbol of pushdown store. So Q naught, W is the string to be processed, and Z0, and after moves, more than one moves, we can write that it will reaches some state which is the final state, and string is exhausted, and alpha is pushdown symbols, whatever may be, and this QF is basically belongs to the final state, and alpha belongs to gamma star, that means the pushdown symbols, and W is any input string on read only input tape, right? So W is any string or input string on read only tape. Okay, so this is how the pushdown automata accepts in terms of final state. Now we'll give an example. Suppose construct, so question is, suppose we have to construct a pushdown automata. So construct a Pushdown automata accepting language L is equal to of the form W C W T, where W belongs to A B star. Clear? And where WT is the reverse of this string. W is any string and WT is the reverse of this string. Okay, by final state. Okay, so now how we can draw the diagram or PDA. Uh, what are the different kind of strings? So form of the string is like that. So here both can be null. Both here W A B can be null. So at that time only the string is C that will be accepted. So string is C which will be accepted. We can write in this way, accepted. Now if only A, then A C A accepted, B C B is also accepted, A B C and its reverse is B A accepted. Again we can write, suppose A A B B C, then its reverse will be B B A A also accepted. So now we have to draw this or construct this PDA. So the main concept is when only C is there, only C will be accepted. So we can draw a PDA. Suppose the initial state is Q0 and after reading C, so suppose it is a Q1 state. So now when your input tape contains only the symbol C, so when your input is C and at that time what is the topmost symbol of PDAs? It will be Z0, and we just replace this Z0 by Z0 and reaches to some state Q1. Now from this state, suppose this is a final state which is QF and string is exhausted. So string is exhausted and at that time the topmost symbol of PDAs is Z0. So we just replace this Z0 by Z0 and reaches to the final state. So C is accepted. Okay. Now look here, C is basically the middle of the string, right? Every string, C is basically the middle of this string. So this is a string, here also this, here also this, here also this. Now before this C, we have to push all these symbols onto the stack. The concept is this, we have to push this onto the PDS, and when C comes, we just moves to the next state, and when B comes, this B and the PDS, at that time the topmost symbol of the PDS will be B. This will be replaced by null. Again this B will be replaced this B by null, and this B A will be replaced by this A by null, and this A will be replaced by this A null, and at that time string will be exhausted and only the topmost symbol at that time will be on push down store, it will be Z0, and so string is exhausted and your topmost symbol is Z0. You just replace this Z0 by Z0 and reaches to the final state QF. How we do this, right? So now we can write, suppose your input is A and at that time your topmost symbol is Z0, just you replace this Z0 by A Z0. So this A we have pushed onto the stack, Z0 and A we have pushed. So now the top just this Z0 is replaced by A Z0. Now when C comes, at that time, obviously the push down store PDAs, the topmost symbol is not Z naught, here it is A, right? So when C comes, and if your input symbol is A, you just replace this A by A and move to this state Q1. We have moved this. Now you are in Q1 state. And in Q1 state, so we have read these two symbols here. AC done. Now your input is A. So when A comes and your input top and topmost symbol is A, just replace this by null. So now if we replace this A by null, that means empty. So now your stack topmost symbol is, remove this actually, your topmost symbol is Z naught, right? So your string is exhausted, your topmost symbol is Z naught, and just replace the Z naught by Z naught and you reach to the final state. So string is exhausted, ACA. Similarly, when B comes, we are discussing for the next string. When B comes, your input is B, and at that type topmost symbol is Z naught. So just replace this B Z naught by B Z naught, right? So now this will be B Z naught. And when C comes, so we have read this B. Now when C comes, but at that time stack topmost symbol is B, so another move will be like this. C, your topmost symbol is B, just replace it by same B. Clear? Basically meaning is B is replaced by B. So the current configuration is this, your topmost symbol is B and you are in Q1 state. And in Q1 state, you have read this B. So when B is your input and stack topmost symbol is B, just replace by this null. So once we replace this by null, that means now your topmost symbol is Z naught, right? So string is exhausted, your topmost symbol is Z naught, and replace this by Z naught and reaches to the final state. Now what happen if the this case are basically occur? So all the symbols before that we have to push onto the stack. Yeah. How we can do this? Initially A, so we can do by using this initial symbol. As we know, stack topmost symbol is Z naught, and when A comes and your topmost symbol is Z naught, just replace by this A Z naught. So first A has been read. Again when another A comes, so we have to include another transition. Your A comes and just replace by this A. So now this A will be replaced by A. So will be this. Now we have read this. When B comes, right, your B comes, but your stack topmost symbol is A. So what happened? Another transition we have to write in this way. When B comes and if your stack topmost symbol is A, just replace this BA. So now B will be here, A will be replaced by BA. So B is basically now the topmost symbol. So it will be B. So this B has been processed. When B comes again, but your stack topmost symbol is B now, so we have to include another transition. B comes, your topmost symbol is B, just write BB. So this B will be replaced by B and B. Okay, just B. So this string, so excluding this C, no, this C will not be pushed onto the stack, only this portion before C. Now we have pushed all the B, right? All the symbols before the C. Now when C comes, at that time, any one of this transition, C comes, at that time stack top symbol is B, just replace this B by B. So it will remain as it same, there is no modification. Now you are in Q1 state and your input symbol is first B. after C first B, this B. So when B comes and stack top symbol is B, it will be replaced by null, right? So your stack configuration now is B, A and Z naught. So when next B comes, again B replaced by null, right? So now your stack content will be A and Z naught. When this A comes and stack top is A, it will be replaced by this null. So now your stack symbols are A and Z naught, and last A when comes, so A is your input and your stack top is A replaced by null. Now your stack symbol is G naught, right? So now string is exhausted. So from Q1 state your string is exhausted, that means this, and stack topmost symbol is Z naught, and you just replace this Z naught by Z naught and reaches to the final state. So string is accepted. The same thing will be happen for B, C, B. So now before C, we need to push all the symbols here into the PDAs or push down store. So when B comes, stack top is Z0. So at that time Z naught. So you have to push onto the stack, right? So Z naught push. When second B comes, and at that time stack top is B. When B comes, stack top is B. So just B. When A comes, stack top is B, right? When A comes, stack top is B. What we need to do? We have to include. When A comes, stack top is B. We just replace this by AB. Okay. So now it will be AB. Now when A comes, stack top is A. A comes, stack top is A, then it will be replaced by AA. Now all the symbols before C, we have pushed all this into the PDAs or push down store. Now when C comes and stack top symbol is A, just replace by just replace this A by A. We just replace this by A, and we move to the Q1 state. And when first A is read and topmost symbol is A, here the topmost symbol is A, just replaced by this null. And when second A comes, replaced by this null. When B comes, replaced by this null. When again B comes, replaced by this null. So now the string is exhausted and your PDS topmost symbol is Z naught, and just replace this Z naught by Z naught and reaches to the final state. So in this way, we can construct a push down automata which accept string by final state. So finally, how we can write? Now we can write in this. So number of state here. So the push down automata M can be written as number of state Q0, Q1 and QF. As we have mentioned here, three states are there: Q0, Q1 and QF. And symbols, input symbols are A, B, small c, and push down symbols A, B and Z naught, and transition is delta. Initial state is Q naught, initial symbol is Z naught, and final state is QF. Okay, and where this delta can be written as, we write all the transition. How? Go to this. Here first is del. You are in Q naught, your input symbol is A and topmost symbol is Z naught, just replaced by and reaches to the state Q naught with push down symbols such A, Z naught. So just we can write in this way: del, you are in Q naught, your input is A and your topmost symbol is this, so it will be in Q naught, A, Z naught. Then next delta will be Q naught, B, Z naught. It will be Q naught, B, Z naught. then delta will be Q naught A. It will be just replaced by Q naught A. Delta Q naught B. It will be Q naught B. And delta Q naught A. It will be Q naught AB. And delta Q naught BA, it will be Q naught BA. And delta Q naught CA is equal to Q1A. And delta Q naught CB is equal to Q1B. Okay. And delta Q naught C Z naught is equal to Q1 and Z naught. And finally delta Q1 and AA, it will be in Q1 replaced by this null, and delta Q1 B, at that time it will be Q1 replaced by this null, and finally del Q1 string is exhausted, stack top is Z naught, you are in QF and Z naught. Clear? So this is the final answer how we have to write when we construct a push down automata by final state. Now we discuss acceptance by null or empty store or stack. Now this acceptance condition include that the stack must be empty as the input string is exhausted. So if we consider that PDA push down automata, symbols are Q, sigma, gamma, del, Q naught, Z naught. Here actually no final states are there, so we have write this is empty. So it is a push down automata, BA push down automata. So the language accepted by this push down automata in terms of null or the empty store, we denote is by this. Suppose n of p, where w is any string belongs to sigma star, so that starts from q naught, string is w, and stack topmost symbol at that time is the z naught. So after moves, the push down status of the push down automata will be some state q dash, which is not a final state, q dash, string is exhausted, or we can write in that way that the stack is empty, or also we can write in that way you are in some state q dash, string is exhausted, at that time topmost symbol is z naught. Clear? So where q dash is any state of q but not a final state, and w is any string on read only tape. Okay. Now concept is the push down store of a PDA with only element suppose is null or z naught is basically considered as empty. We consider it is an empty stack. Okay. Now we'll give an example how the PDA, suppose we give an example, uh, construct a PDA accepting set of all string all strings over AB with equal number of A's and B's by empty stack. Okay. Now this equal number of string means it will be like that: A B B A B, or A B or B A or B A B or A B, all are basically equal number of A's and B's. So these strings will be accepted by this PDA in terms of empty stack. So look, when A comes, we just push it onto the stack, and B comes, we just remove it. Similarly, when B comes, we just push it, and A comes, we just remove it. And when A comes, again at that time stack top is a major factor, so stack top is A, we just push A, and when B comes or different symbol comes, at that time we have to remove it. So the concept is like that. We can design in that way. Suppose this, so this is suppose our initial state Q0, and when A comes, right, suppose your pushdown store is this PDS, and we know that initial symbol is Z0. So when A comes, suppose we have to accept this AB. Now when A comes, and at that time stack top is Z0, just we have to push it. We push it, right? So it will be A Z0. And when B comes, and at that time stack topmost symbol is A. So when B comes, stack topmost symbol is J, just replace this by null. So we just replace this by null, right? So now your string is exhausted and your PDS is also empty. So string is accepted. Z0, as we have mentioned, that stack with only one element Z0 is considered to be empty. Okay. Now when BA comes, right, when B comes, the B is the first symbol. So when B comes and stack top is Z0, just we write B Z0. So here it will be this. Now when A comes, but at that time stack topmost symbol is B. Okay, so we can write when A comes, stack topmost symbol is B, just replaced by this null. Okay, again this will be replaced by null, and stack symbol is Z0, and string is exhausted, so it is accepted. Now when A comes, what happened? When A comes, so first symbol when A comes, stack top symbol is Z0, so it will be A Z0. When again A comes, but at that time stack top symbol is A, so we can write A stack. If stack top symbol is A, just we push it A, so it will be this. Now when B comes, stack top is A, just replaced by this null. When second B comes, stack top is A, replaced by this null, and string is exhausted, and your PDS symbol is only Z0, so string is accepted. Now when AB, this string AB, when A comes, we push into this A Z0. When B comes, replaced by this null. Again, when A comes, stack top is A, stack top is Z naught, sorry, A Z naught. When B comes, replaced by this null. So string is exhausted. Similarly, the B A also same. Here B, here this for this string, when B comes, okay, and stack top is Z naught, so B Z naught will be there. When A comes, stack top is B. When A comes, stack top is B, it will be replaced by this null. So we replace it by null. Now, when again A comes, stack top is Z naught, so it will be A Z naught. But when B comes, stack top is A, so it will be replaced by this null. String is exhausted, and your topmost symbol is PDAs is only the single element, that is Z naught. So string is accepted. So in this way, string can be accepted by empty stack. So thank you.